So chemical bonding too. Good quote though, again, about theories. No theory ever solves all of the puzzles with which it is confronted at a given time, nor are all the solutions already achieved often perfect. Yeah, but like we've used Lewis theory to predict structures of things, and that's fine. Works pretty good for some of the stuff we talked about, and we're going to talk about how it doesn't work and how it's not fine. VSEPR theory. Yes, I know it's VSEPR, so it should be like VSEPR, but it's pronounced VSEPR because that's easier to say. So valence shell electron repulsion theory ultimately comes down to one thing, that electrons don't like each other and they get as far away apart as possible. That is what this entire theory boils down to. It's very simple, very easy. You might need to brush up on your 3D spatial reasoning because that helps a lot for this. So for these molecular shapes, we've got electron groups, which are lone pairs, and single bonds, and double bonds, and triple bonds, and even a single electron in the rare case. Those are all electron groups. They're groups of electron around an atom. So a single bond counts as one electron group, a double bond counts as one electron group, triple bond counts as one electron group. I know that can be a little bit confusing because when you do formal charges, you count each of the lines. So what we're concerned about are the repulsions between electron groups on interior atoms, and that's what's defining the geometry. So for this cartoon here, these electron groups that are around that central atom try to spread out. They try to get away from each other. They like their space. So our preferred geometries will have the maximum separation, and we'll talk about those separations in terms of degrees. So how many degrees are they separated by? So this is, in this case, would be 120, assuming that they're all equal and they look like it. Okay, so this is going to kind of come down to, and I would encourage you to treat these in your mind as groups. So we're going to talk about a bunch of different electron groups. So if you have two electron groups, so that's either two bonds or a bond and a lone pair, there's only one geometry that you can have. And that's a linear geometry. So you can, confirmed by observation, you can look at it. Actually, that's what these balloons are up here for. Yeah, linear geometry. So if we had a central atom in the middle here, that would be the beryllium, and they got chlorine on either side. I can make them go to the same side, but they really don't want to. Just in their natural state, they want to be separated by 180 degrees. So linear geometry, it's the simplest one. And then if I removed one of those balloons, which I'm not going to, actually, then we just have, yeah, I guess that would be like, that's the lone pair. But it would be kind of like this if this was the single bond. So you'd have central atom here and then the balloon is here. The only shape you can make with 2 points is a line. So it's linear, all right? And we just get more complicated from here. Oh, except Lewis structure for CO2. So sometimes the Lewis structure and VSEPR theory are going to line up. So two electron groups still has a linear geometry. If we move up to 3 electron groups, every electron group more that we have, the more complexity that we can have. And it works out to be n minus 1. So if we have 3 electron groups, how many different shapes can we have? If we can have 1 fewer shape than we do electron groups, 2. 3, actually, yeah, 3 minus 1 is 2. I went through and I graded the pre-lab for the potassium permanganate titration lab, and a bunch of you guys had written, like you had to calculate the number of milliliters to do or whatever, so you got 15 milliliters, and then you said plus 3 milliliters, and then you wrote 17. I saw a bunch of people in the same row just saying something didn't add up there, literally. Anyways, so yeah, it kind of works out to be n minus 1. So if we have 3 groups, 3 atoms, then you get trigonal planar. It's flat. And again, I can try and force these to all be on the same side. They don't want to. They repel each other. They don't want to. And the maximum separation that you can have, 120 degrees. Things will get slightly more complicated when we add lone pairs. Formaldehyde, question? Yes, it can. Yeah. I haven't got a polarity yet, but yes. We'll have to modify my rules from Chem 20 a little bit, but formaldehyde, also 3 electron groups. All of them are atoms, so our electron geometry or molecular geometry are the same. Now, in this case, though, the oxygen is more electronegative than the hydrogens. And so it's going to actually push away the hydrogens from the oxygen a little bit more than 120 degrees. Because the hydrogens, not very electronegative, not as much repulsive force, they can get closer to each other, and they want to be farther away from the oxygen. So slightly different bond angles. So if you have a central atom and a 3-atom molecule forms 2 double bonds, has no lone pairs, what is the geometry of the molecule? Linear. So we're assuming, so if you have 2, then you could have lone pairs, and then you might get something else. Yeah, if it had lone pairs, it would. But we'll get there. Doesn't matter what they are. Especially if it's linear, it doesn't matter. So like in our trigonal planar here, it matters the slightest amount because these angles change a little bit. It's still trigonal planar. It's still really close to that. And again, this is because the oxygen is more electronegative than the hydrogens. The maximum, like for all of them, would be 120. For them to have equal separation, they can't get farther than 120. But this is unequal, so the hydrogens get pushed closer together. Yeah. So this is because it's more electronegative, but what if we had something like this? What if I told you that this one is more electronegative than the other one? Can they get any farther apart? No, 180 degrees is as far apart as they can get. All right, so if we move up to 4 electron groups, and 4 electron groups is as far as you went in Chem 20. That's this one, that's the tetrahedral. So molecules of 4 or more groups are 3-dimensional, and when we mean 3-dimensional, it's that this is flat. Yes, these are balloons. Yes, we're all living in 3D. And I don't know, when I did this in Chem 20, some people would give me tetrahedrals that were written like a flat cross, which is square planar. I was like, no, it needs to be 3D. This is what I meant, right? So this is 3 dimensions. The balloon analogy, we have actual balloons. Right, so these balloons are representing our electron groups. So for linear, it's 180. For trigonal planar, it's 120. But again, in the same plane, you can't get any farther apart than 120 degrees. So to get any farther apart, it has to move to a 3rd plane. So what do you think this bond angle would be between these? It's more than 90. Because if it was 90, then it would just be, who's looking ahead? That would be 90s. This is more than 90 though, because we can do 90 in a single plane. So yeah, it's 109.5. 109.5. So each of these balloons, theoretically, would be 190 or 109.5 degrees apart from each other. Wow. So that's tetrahedral. Methane has this configuration. So, of course, when we draw the Lewis structures, it's flat. When you look at this, that's 90 degrees, which is why it's not the correct geometry, because we can get this 109.5, which is more. So, hydrogen cyanide, what would the geometry be? Yeah, so we're thinking about, always thinking about the central atom here. So it's linear. There's only two groups, and this is where that 3D spatial reasoning comes in. That if you have two groups and they're moving around a single point in space, what's the farthest apart that they can get? Opposite sides of the point. Can't get any farther apart, so it's linear. And it doesn't matter that there's any electronegativity difference between these two either. That angle is going to be 180 degrees. Literally can't get farther apart. Yeah. If anything, maybe the bond lengths would be a little different compared to just like a carbon-nitrogen triple bond by itself or a carbon-hydrogen bond. Now, we venture out into the unknown, the previously unexplored. What if we have 5 electron groups? No, that's not 5 electron groups. Oh, we don't have 5 electron groups. I guess we could do this. 5 electron groups. So it's trigonal bipyramidal. So you can think of it as 2 pyramids with 3 sides stacked on top of each other. All right, so the top pyramid is right here. That's a pyramid, and then there's another pyramid on the bottom. And this ends up being a combination. So we've got 2 different bond distances. And we call these axial and equatorial. So the 2, the top and the bottom, essentially are going to be your axial, because they're an axis, because you could take this thing and you could spin it like a top. And if you spin it like a top, then those ones on the outside, those are on the equator of that shape, so those are equatorial. So the separation between each of the equatorial ones is going to be, essentially, your trigonal planar. But now there's an electron group on the top and an electron group on the bottom. But because we have an electron group on both sides, they cancel each other out and can push these to be flat. So our optimum separation becomes a combination of 120 degrees and 90 degrees. And then the last one that we're going to talk about is the octahedral. So now it's 2 4-sided pyramids, but we don't call this like square. Yeah, we'll use something else. Quadrilateral, bipyramidal or something. So that's what, this one's done here. So that's the octahedral. So now it's very much like the trigonal bipyramidal, except that we have 4 things that are all separated, each by 90 degrees. And then that makes all of our bonds 90 degrees, or all of our electron groups 90 degrees apart. And these can only happen with expanded octets. Okay. All right, so let's determine the molecular geometry of carbon tetrachloride. So the first step is going to be Lewis structure. So we need to figure out how many electron groups we're going to have. Carbon and then chlorine. These are 7 times 4, and 4 times 1. So 4, 28, 32. And then our chlorines. And then that's minus 8, 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So how many electron groups are there? 4. Yeah. The only ones we care about here are the ones around the central atom. Yeah. The lone pairs on the chlorines don't matter. They won't change the shape. Yes. Now, on something like this, yeah, so this would be 4 electron groups as a tetrahedral. And what are the bond angles for a tetrahedral? 109.5? No. That's not 109.5. Something else. So what if I did this? This dirty ozone depleter. What's the shape? Same thing. Yes. So they're not all going to be 109.5 because chlorine's more electronegative. So between the chlorine and each of the hydrogens, what's the bond going to be? Approximately. Yeah. Best we can say is greater than 109.5. So this is like chlorine to hydrogen. So then what about between the hydrogens? Less than 109. It's a zero-sum game. There's only 360 degrees to be had. Somebody takes more, somebody gets less. Yeah, so it pushes those together. Okay, so so chlorine pushes these apart because it's more electronegative, right? Or it pushes the hydrogens farther away. What if I draw out something like this? It's not a ghost, don't be scared. It's just a lone pair. It's just lonely. Just like ghosts, sorry. Compared to a chlorine, how much more electronegative is a lone pair? Do you want to say what? Yeah, it's just pure negative charge, essentially. So it's going to be more electronegative. And so it will push these apart even more than the chlorine would. The other thing, though, is what would this electron geometry be? How many electron groups do we have? Lone pairs are electron groups. And it's a lone pair on the central atom. Yes. Yeah. So the electron geometry only depends on electron groups. So this will be tetrahedral. Now our molecular geometry, yeah, it only depends on the arrangement of the atoms. So this would be trigonal. Yes. Trigonal pyramidal, if you're trying to be fancy. So lone pairs change things a little bit, but they still come down to the same basic shapes. So in essence, this is a tetrahedral. We've just replaced one of our solid atom nuclei with a nebulous cloud of electrons. You could even think of it as a ghost of the atom that might have been. Okay, so 4 electron groups, the lone pair. Hey, look at that. It's that molecule that I drew. So ammonia, 4 electron groups, again, use Lewis structures to get to the number of electron groups. Does a pretty good job of that. 3 single bonds and 1 lone pair means that we have 3 bonding groups and one lone pair. So it gives us the trigonal pyramidal. And what if we pluck off another one of those hydrogens and replace it with another lone pair? Yeah, it'll be bent because the angle between them will still be about 109.5. Oh, yeah, okay, so here's the lone pairs, right? Pure electronegativity pushes these farther away, so you actually get an angle of 107. So even less than if it was a chlorine. Now, for water's got 2 lone pairs, and it's got 2 hydrogens, 2 atoms, still essentially a tetrahedral. So this is what I was saying, if your 3D spatial reasoning skills are really good, you can just picture a tetrahedral in your mind and pluck the hydrogens off to get these new shapes. And some of them are pretty self-descriptive. So this shape is bent. If you look at the shape of the atoms, it's not a line, it's a bent line, which is bent. And then because we've got 2 lone pairs here pushing against the hydrogens, instead of just 1 lone pair pushing against 3 hydrogens, now our bond angle gets even smaller, so 104.5. Yeah, so the electron groups tells you what the electron geometry is. So tetrahedral, but yeah. Not the lone pairs. The atoms determine the molecular geometry. Yeah, it'll have to be specified. Which one are you looking for? Yeah, like I did before. So I said the Cl to hydrogens is larger than 109.5. The hydrogen angle is going to be less than 109.5. Yeah. So it'll depend on what I'm asking about. Although, actually, here if I ask what the bond angle is, it's the angle between the actual bonds. Right? So here we have lone pairs, we're not counting those angles, but the distance between the two things that are bonded. It's just in the case of the carbon tetrachloride that I'd have to specify between the chlorine to hydrogen or the hydrogen to hydrogen. So yeah, 4 electron groups, you're just taking your tetrahedral and then remove one or replace one with a lone pair or replace 2 with lone pairs. So what's the molecular geometry of a molecule whose central atom has 3 bonding groups and 1 lone pair? Trigonal pyramidal. Yeah. Another way that we can, wait, do we talk about this? I don't remember seeing it actually. So we could also use a shorthand for this. So if we write AX3E, A is your central atom, and attached to that, there's 3 atoms, those are the X's. The lone pairs is just the E. So this would be trigonal pyramidal. What if this was AX2E2? Bent. So we got, it's like water, like up here. So the E means 2 lone pairs. And then the X subscript 2 means that we've got 2 things that are bound to the central atom. So that molecular geometry is bent. Because the lone pairs push the atoms down. It's like this would be if we just had the 2 hydrogens. Wait, do I have 2 lone pairs? Oh no, I don't have 2 lone pairs. I guess I could do it with these. These would be the lone pairs. So, like this, maybe what you're thinking, we've got 2 things that are attached, but these lone pairs also exert an influence. So they force the blue ones down to make the bent shape. Yeah. So that's what's happening with those. Okay, so if we go to 5 electron groups, these are things get a little bit weird and it's a little bit harder to visualize. So SF4, and then this would also be AX4E. You get a seesaw. Now, there's 2 places in theory that we could put the lone pair, but this is wrong. And it's wrong because in this case, now the lone pair has a 90-degree angle between it and all of the fluorines. So there's 3. This actually comes into what the lab's about a little bit. So we call these, what are they on the worksheet? I want to use the same term. Oh, lone pair, bonding pair, right. So this is our lone pair, these are bonding pairs, right? So this is a lone pair, bonding pair, lone pair, bonding pair, lone pair, bonding pair. So an L, capital P, LP, BP interaction. And so there's 3 of those that are 90 degrees. But if I flip over to this one, our lone pair, bonding pair interaction. Yeah, so now this one is 90 degrees, and this one is 90 degrees. So there's only 2 of those. So there's fewer 90-degree interactions. So it's optimal, or more optimal at least, to put the lone pair on the side as one of the equatorial electron groups. And so then you get this shape. Oops. If I turn it that way, looks like a seesaw. All right, so a seesaw. Yeah, so that's the seesaw. AX4E. 2 lone pairs now. Similar thing. We're not going to put one of these lone pairs on an end, so to speak, right? It's not going to be axial, because it's going to be more optimal to put it on the sides. Yeah, you're going to get plenty of practice in the lab. And so that's T shape, because it makes a T. It's a T pose. So how would I write this in like the AXE notation? E2. Yeah. Yep. E is a number of lone pairs. So then if we move to 3 lone pairs, and again, we're just taking the trigonal bipyramidal and plucking atoms off and replacing them with lone pairs. If we get 3, then all of these become equatorial, because that's the best separation they can get, and you end up with a linear molecular geometry. And let me zoom in on this. So let me ask you this. Is this polar or nonpolar? But the central atom has lone pairs. But they're equal. They're canceling each other out. They're all directly opposite of each other. Whoops. So this would be non. Possibly. Yeah, sometimes most of the time you can figure this out if there are lone pairs. If we go back even one step right here, this is polar, because those lone pairs are not directly opposite each other. So you're going to have a difference in electronegativity across one axis of that atom. But as soon as they're all equal, then it's going to be nonpolar. And we haven't talked about polarity yet, but the rule that I taught a bunch of you in Chem 20 was that if there are lone pairs on the central atom, it's polar. And this is an exception to that. Okay, so let's go through these 6 electron groups, lone pairs real quick. I always thought this one was funny because it looks like a 4-legged thing that just splatted on the ground. It just did the 4-way splits. Yeah, it looks like a stuffed animal. You just drop it and they just spread out. So this is square pyramidal. So there's a trigonal pyramidal where it's 3 sides. This is square pyramidal. And then this is AX5E. So you can also figure out what the root shape of these things is going to be based on the number of X and E's. Add those up. We have 6. An octahedral has 6 atoms, which is the base. And it says here that the lone pair could be in any position, but why is that? Every single one of them is 90 degrees. So it doesn't matter where the lone pair goes. And this one is trippy to think about, because if I move that lone pair and swap it with one of the atoms, then I can rotate the shape and get exactly the same picture back. And then if we go to this one, here's another exception to that polarity rule. And again, we've got electron groups, lone pairs. We've got lone pairs that are directly opposite each other. Okay, I just realized, I was like, wait, did I start recording? I did. So there is a table. Oh yeah, sorry, this is called square planar. So we've taken the top off the pyramid. Now it's just the base of the pyramid. So there's this whole chart. There's a bunch of them. And then these bonding groups and lone pairs, those are your X and your E for your AXE notation. These, actually, let me ask you this. Why can't we just take off another one of these and replace it with another lone pair? But it's too many electrons, too many cooks. You'd have to have some central atom. Yeah, what am I trying to say? The formal charge on the central atom would be ridiculous, essentially. Yeah, Cohen. Yeah. I don't think I gave it one. We are not going to actually talk about what those shapes would be called as a whole, but rather thinking about one of those A atoms inside of that larger molecule. Aside from that, no, I don't think that we need the A, but you could use that as a, yeah. Right. I think that's a reasonable guess as to why it would be there. So if we had a molecule with 6 electron groups that is confined to 2 dimensions, so it's flat, so hexagonal planar geometry, if 2 of the 6 groups are lone pairs, where are they located? Why 1, 4? As far apart as possible. Plus, it's the only option that's only one of these options, right? Because we could do 2, 3 or 2, 3 this way, but that doesn't matter. It's just because of the way that this noted them, 1, 4 and then 2, 3 or 2, 3, each of those would be equivalent, so it would be redundant to say all of them. But you wouldn't do 1 and 2, because here this 1 and 2 would be that one, or it would be on the other side 1 and 2. That's too close. And 1 and 3, like those are equivalent between 1, 3 on one side, 1, 3 on the other are equivalent. Yeah. It's just to narrow the options. All right, so the geometry of the molecule is determined by the number of electron groups on the central atom, and that number of electron groups determined from the Lewis structure. So this is building on Lewis structures. And then each of the following counts as 1 electron group: lone pairs, single bonds, double bonds, triple bonds, and in the rare case, single electrons. And then the geometry of the electron group is determined by the repulsions. So how far away can you get everything? And try to get lone pairs especially as far away from any other bonding groups. And then your bond angles can change a little bit. So which statement is always true? A rare Sith moment dealing in absolutes. Which statement is always true according to VSEPR theory? That was fast. Confidence, I like it. Yeah, so shape of the molecule is determined by only repulsions among bonding electron groups? Read the rest of them. Read the rest of them, let me know. I think your head and your heart were in the right spot. It's all of the bonding groups, right? You're focused on the repulsions. Right? It's only the repulsions between all the groups on the central atom. Oh yeah, just some steps. And then we're going to skip the practice problems here because we're going to start working on the lab. Draw a Lewis structure for the molecule to determine the total number of electron groups around the central atom. Do the bonding groups, number of lone pairs around the central atom, and then you can refer to that table. Let me just make sure that we're not missing something else for this. No, I think we're good. I think that covers us for all of this. Man, I really wanted to show you this meme today. Where is it? All right, so you want to know why there's so many weird rules and exceptions? So there is a reason. I'm just not qualified to talk about it. There's all the quantum physics, and we've covered some of this, like some of the quantum physics between some of the exceptions that you've learned. But as you keep going, there's going to be more and more exceptions.